Hi everyone. We introduced hybridization in the previous video, looking mainly at carbon and its 4 single bonds. But we also know that carbon can create double bonds and triple bonds. And the way that the carbon hybridizes in those situations are going to be different. And so in this video, I want to talk about hybridization in molecules that have these double and triple bonds. Another way to say that is that they have what's called a pi bond. Okay, let me just remind us that when we have carbon and there are 4 single bonds, that carbon is hybridized. Do you remember what kind of hybridization this carbon has? This carbon has sp3 hybridization. sp3 hybridized. And because we are mixing 4 atomic orbitals, an s, a p, and a p, we get 4 hybrid orbitals. And the way that we draw carbon now with its hybrid orbitals is like this, with the lobes that are sp3 arranged in a tetrahedral arrangement. So all of these blue lobes are sp3 orbitals. And you know that carbon has 4 valence electrons. 1, 2, 3, 4. When we take a look at nitrogen, you know that nitrogen has a lone pair, but that lone pair is one of the 4 balloons. So nitrogen is also sp3. But in this case, one of the balloons, one of the sp3 orbitals has a lone pair. So now nitrogen, we could fit 5 valence electrons, and so forth. I think on the last video I asked you all to try water, H2O. H2O also, its electron domains are arranged in a tetrahedral shape. Okay? But we also know that carbon can form a double bond, and other atoms can form a double bond. And today, we're going to look at this example first. And also, we're going to look at an example where carbon and nitrogen share a triple bond. Okay? It's still important for us to understand the valence electrons and where they are and how many we have. Nitrogen, to fulfill the octet rule, has a lone pair there and 3 bonds. Carbon still has 4 bonds in this case. Carbons still have 4 bonds in this case as well. Okay, so let's do the hybridization of this carbon right here. Before we draw any type of energy coordinate diagram, let us guess what the hybridization of this carbon is right here. Now, do you remember the trick? The trick was, since that carbon for methane has 4 balloons, okay, I like to call the electron domains or the electron pairs balloons, right? This comes from VSEPR theory, valence shell electron pair repulsion. So this has 4 balloons. Well, in this case, remember how I said a double bond also is encompassed by 1 balloon as well. So this is 3 balloons, right? And how about this nitrogen here? This nitrogen is 4 balloons. This oxygen here is 4 balloons because you got to remember it has 2 lone pairs as well. Okay. But let's focus on that's in the past. If you're not very clear on what I just did up here on the top of the page, all of this is in a previous video, 07F20. All right, 3 balloons. That indicates that the hybridization is sp2 because it mixes an s, a p, and a p. 3 atomic orbitals mix to create 3 hybrid orbitals. Okay. Let me show you now that diagram. It's really have energy on the y-axis, and we're going to put in Um, so hmm, at the very end of the last video, I started to use boxes to indicate the orbitals. Why don't we practice that? Okay, instead of drawing the shape of the orbitals, like the s orbital and p orbital, let me just put boxes. 2s, still in carbon, so carbon is in the second period, and we have the p's, 3p's. Oops, not 3p's. We have three 2p orbitals. Okay. Remember what was the strategy here? The strategy here was this side is the atomic orbitals. And then when we mix them, we get the hybrid orbitals on the right side. Mix. Okay. So before hybridization, your 4 valence electrons for carbon exist 2 in the 2s and 2 in the 2p, but they're separated because of Hund's rule. I got a mix, an S, a P, and a P. It doesn't matter which P's you choose, okay? I'll just pick it. Again, it doesn't matter because we're going to reassign these electrons anyway, okay? Remember the rule? If you mix 3 atomic orbitals, you get 3 hybrid orbitals. And those hybrid orbitals are here. The thing is, we have a unhybridized p orbital. So that unhybridized p orbital is in the same level as where it originally was, and it's right here. And this is a p orbital, right? These are your sp2 orbitals. When you fill in the valence electrons, right, these are now the hybrid orbitals, at least these 3. When you fill up the orbitals here, we're still using Hund's rule, but we're going to be a little bit flexible and say that, well, these 2 energies are pretty close together. So we're going to consider the p orbital here also as equal energy as the sp2 orbitals. So Hund's rule says you singly fill before you doubly fill. Hence, for our 4 valence electrons, we will singly fill each of these 4. Because again, we are considering this p orbital close enough in energy, right? These 2 are not as close. So we use Hund's rule and we doubly fill this, and then we go to the next level. What do we have here? We have a situation where we have 3 balloons. Okay, this is unhybridized. So literally, what I have here is a carbon. I'll do it on this side. That has 3 balloons. 1. Do you remember 3 balloons are arranged in the trigonal planar orientation? Do I have that chart? Let's see. Here it is. The trigonal planar family. Okay, if you have 3 balloons, right, trigonal planar. And here we, again, 3 balloons up here also. But where's that p orbital? I like to draw the p orbital in red. And remember, it's a dumbbell. There are 2 lobes. And that electron can be in either of the 2 lobes. But when we fill in the dots for the electrons, okay, those are your 4 valence electrons. And we have a p orbital right here. All the blue ones are sp2, right? sp2. And we have 3 of them. Well, that carbon, I'm going to say, represents the carbon on the left. The carbon on the right also is sp2 hybridized. So maybe I could also do something like that, sp2 hybridized. So here's the carbon on the right, and it's also sp2 hybridized, but I'm going to turn it around so its sp2 orbitals can overlap with the one on the carbon on the left. And then we still have the same geometry, trigonal planar. We still have a p orbital that's unhybridized. Dot. It doesn't matter where you put the dot in the p orbital. I'll put it also on top. Dot, dot. You see how this allows for valence bond theory to work? Because look at how many half-filled orbitals we have. So we could put a hydrogen here to complete the bond. 2 electrons, right? And this is H. So we're going to have H's for each of these sigma bonds here. Okay. We're almost done with the cartoon picture. We definitely see a bond between the 2 sp2 orbitals of each carbon. But also, as you bring these carbons closer together, you're going to get overlap between the p orbitals. And a lot of times people draw them separate, kind of spread apart for clarity. But in real life, they are pretty close together, and these lobes touch, and these lobes touch also. Look how many electrons they're sharing when you overlap the p orbitals. You're sharing 2 electrons. Isn't that a bond as well? That's the second line up here. We have the first line here, sigma bond, and we have a second line formed by the overlap of the p orbitals. Now, if you think about it or try to visualize it, the electrons that are in the p orbitals that are now being shared, they actually never are very close to the middle, to the bond axis. Remember the definition for sigma and pi? Sigma, a sigma bond, is that the electrons are close to or on average on the bond axis. On average along bond axis. But the pi bond is the overlap is not in the bond axis. So here the electrons on average are not along bond axis. Okay? And the way I like to think about it is this food item right here. And we have something in the center. So here, the hot dog, right? The hot dog is the sigma bond. And the cornbread coating is the pi bond, right? So this is a corn dog. The electrons in the pi bond are around the bond axis. So ultimately, there's your hybridization. It's sp2. And ultimately, if you have this molecule and you are asked to describe what is mixing, not mixing, I got to use my terms very carefully, what orbitals are overlapping to form this bond right there. Let's take care of the sigma. Looking at this picture in the upper right, we have a sigma bond that is created by a carbon, and then some people use subscripts. I probably won't. So sp2 overlapping an orbital from carbon that's also sp2. You see how that works? I'm literally reading this picture here. sp2, sp2, right? These two are sp2. But we also have a pi bond, and I'll do this in purple. We have a pi bond between a carbon that has a p orbital overlapping the p orbital of the other carbon. So we have Cp, Cp. Okay? So just remember that a double bond is going to be a sigma bond and a pi bond, because there are some problems where you have to indicate, well, how many pi bonds are in this molecule and how many sigma bonds are in this molecule. Okay. Real quickly, you could check yourself. Pi bond, oops, let me draw these two lone pairs. Pi bond and pi bond. So there are 2 pi bonds. And there are 1. So there's a sigma bond right here. 2, 3, 4, another sigma bond, 5, 6. there are 6 sigma bonds for a total of what? For a total of 8. So let's double check. 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Now, as long as we have this molecule, before we get to our, what is this? This is hydrocyanic acid. Let's practice this oxygen right here. So I'm pointing to the oxygen, not the lone pair. That has 3 balloons. 1, 2, 3. You will know that this oxygen is sp2 hybridized. Okay, and it has sp2 hybridized orbitals. This nitrogen right here, 1, 2, 3, that is sp2 hybridized as well. Okay, now sp2 is synonymous with trigonal planar. But remember, trigonal planar is the family, is the shape made by the electron domains. If you have a lone pair, right, then that geometry is bent. The electron domain, right, the electron domain shape is trigonal planar, but the molecular geometry for a case like this is bent. And we do have that case right here. See? One of the balloons is a lone pair. So the geometry around this nitrogen is bent, but the electron domain shape is trigonal planar. Okay, do you see how that works? Now, I wouldn't describe a geometry around this oxygen because that oxygen is not a central atom, right? We don't have more than one atom around this oxygen. So there is no shape, molecular geometry for this oxygen. But this nitrogen, yes, you have these 2 atoms flanking it. All right, are you ready? Understanding this picture right here, what we mix is going to help us figure out what to do with this molecule right here. But you know that it all starts with a proper Lewis structure. And after the proper Lewis structure, it continues with a proper identification of the number of balloons. The proper Lewis structure for hydrocyanic acid is this, and it has a lone pair. The number of balloons for this carbon is 2 balloons. So hence, we have a new type of hybridization that we have not seen yet. sp2. 1, 2. What about this nitrogen right here? That nitrogen has 2 balloons as well. Okay. Those 2 atoms being connected with a triple bond, they're both sp. Before we look at the energy diagram, similar to this, can you predict how many p orbitals are unhybridized if I am only mixing one of the p orbitals? Do you realize that since I'm only mixing one of the 3 p orbitals, I now have 2 unhybridized p orbitals? Just to mix it up, and so you have familiarity with both types of energy diagrams, instead of using boxes now, let me literally draw the shapes of the orbitals. Okay, we're still with carbon. We have the 2s and the 2p, and we have 3 of them. Okay. It's the same drawing, same concept as this. Instead of using boxes, I'm using the shape of the orbitals. Same concept. Fill in your valence electrons. But here's the difference. Because I'm mixing just an S and a P only, mix. Again, it's arbitrary. You can pick any of these 3, but for convenience, and you'll see why, I'm going to pick these 2 and leave the other 2 p orbitals unhybridized. When you mix 2 atomic orbitals, what was the rule? You get the same number of hybrid orbitals. And since we're making 2 hybrid orbitals, those are separated by 180 degrees. So I'm going to draw the two lobes like this. Those are your two sp hybrid orbitals. Look what happens to the unhybridized p orbitals. You just carry them onto the same level. So we have a p orbital here, and I chose this one to be unhybridized, and a p orbital here. If you use Hund's rule, 1, 2, 3, 4. 4 valence electrons, correct? All right, let's, so we have a carbon, and literally, you know that a molecule that has two balloons will go linear. We saw that for carbon dioxide right here. Linear, two balloons, literally, those are balloons. They separate it as 180 degrees. But look at the p orbitals. We have one, I chose the one that's going vertical to be unhybridized, and the one going in out of the plane is unhybridized. It didn't matter which one you choose, because if you're very good at three-dimensional and visualization, you could rotate this, and those two lobes will stay right in the axis, and you could change the orientation of these p orbitals. So it doesn't matter whether you choose X, Y, or Z. You just have to make sure that there are two of them unhybridized. If you fill in your valence electrons, the same way we did it here, your dots are now there. So all I'm doing is overlaying these orbitals onto a carbon nucleus. But look at nitrogen. Nitrogen has the same situation. So nitrogen is also sp, and I will, let me draw this a little bit closer. We have overlap here, not overlap, but we have a lobe there. And we have the p orbitals. P, 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 P. So here's the trick. Nitrogen has 5 valence electrons. You could fit one there, make a bond 1. You could fit one here to make a bond with this p orbital. So it is going to get a little bit crowded. You could fit one here to make these two p orbitals make a bond. That's only 3. You realize that we have the fourth and the fifth one in the same sp orbital. So the lone pair, we're not going to have to worry about this for this course, but the lone pair is in an sp hybridized orbital. That is the picture. Oh, we're not done yet. We have a hydrogen connected to the carbon. That is the full picture of the orbitals and their overlapping. And let me just label this as the s orbital. Okay. I know it's crowded, so we're not going to label every single sp orbital, especially the ones in the middle. Okay, but we have all the valence electrons here. I guarantee that. We have 1 plus 4 is 5, plus another 5, that's 10, plus these two electrons, that's 12. 12 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I count this right? 4 plus 1 is 5. Oh, I shouldn't count those lone pairs. I already said that nitrogen has 5 valence electrons. This is what happens when you rush. 1 plus 4 plus 5 equals 10. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the last part is we have the picture, the cartoon. Let us assign what orbitals are overlapped to make that bond. And literally, we're just going to read the picture. The two blue sp orbitals, they make a sigma bond. Carbon sp orbital overlapping with nitrogen sp orbital. Then we have the pi bond. And I'm going to look at the vertical p's first. See, what's happening is you have the two p orbitals that come in like this and overlap. The other p orbitals are in and out of the plane, and they come in like this. Okay, so we do have two pi bonds. And you don't have to indicate which direction they're in. You just have to know that they are p orbitals that are overlapping. And we have two of them. See, one of them indicates the ones that are vertical, and the other one represents the ones that are coming in and out of the paper. Okay, so that is a description of a triple bond. A triple bond is a sigma bond for sure, and the other bonds, the extra bonds, are pi bonds, pi and pi. Okay, so there are other practice that you can do, like literally from this video, right? You could practice this. You could ask yourself, what is making this bond? It's definitely a pi and a sigma, but you have to describe also the orbitals that are making the pi bond and the sigma bond. Just remember that one of the atoms is oxygen, okay? Or this one. What orbitals are overlapping to make that double bond? And you can do all the bonds, actually. You could describe all the bonds. Now that you have an idea how to draw the cartoon picture. I feel like if you practice enough, you'll find shortcuts, and you won't need to draw this fully. You will know that this oxygen is sp2 hybridized. You will know that there's a pi bond here that's the overlap between two p orbitals. Okay, with practice that will become automatic.